Welcome to Module 11 in our series on artificial intelligence. This module compares two optimization methods relevant to machine learning, batch and stochastic gradient descent. If you're looking to learn more about tensors, a topic that's important to anyone who works in machine learning, please check out my book. You can see two QR codes at the bottom of the page here. One leads you to a sample of the text, and the other one provides a link to purchase. We begin with that comparison of the batch and stochastic gradient descent methods. More specifically, we're going to discuss three implementations: the single element stochastic gradient descent, the mini batch stochastic gradient descent, as well as the complete batch gradient descent. Most of the machine learning examples that we've discussed so far have employed the single element stochastic gradient descent method. Therefore, we begin our discussion here, and we will take a closer look at the update expression shown below. For this implementation, an updated parameter array at iteration it plus 1, and we can see that down here it's represented as theta with the superscript it plus 1. This would be the parameter array for the current iteration with the superscript it. So the updated parameter array at iteration it plus 1 is computed using the partial derivative or gradient of the objective function that we want to minimize taken with respect to our parameter array, and then evaluated for a single set of inputs x that are taken from one randomly chosen sample, which we denote by S, within the training data set. So let's take a closer look at this update expression. What we see is that for gradient descent, we want to calculate an updated set of parameter values that correspond to iteration it plus 1. This is generalized for any iteration. That is defined as the set of parameter values for the previous iteration it minus the product of two factors. First, we have the learning rate alpha, and then we have this gradient or this partial derivative of the objective function taken with respect to theta. Now, this is a numerical expression, right? We want to generate a numerical value for our updated parameter array, and as such, we need to evaluate the partial derivative, and to do that, we supply to it a set of inputs referred to as x. Now, these inputs will be chosen randomly from the training data set, and to indicate which sample we're working with, we use the superscript brackets with s, or we can say s of it, where this is simply saying that the sample is associated with the current iteration. Now, this method relies on the law of large numbers. We see that each iteration considers only a very small piece of the overall system behavior, right? For a system that may have hundreds, thousands, or millions of training data samples, it doesn't seem like a great idea to perform an update based on one. However, after many iterations using randomly chosen samples, we expect that the parameter values will converge to that expected or associated with the overall system behavior. But isn't there an advantage, potentially, to using more than one training sample per iteration? And the answer is yes. Doing so may provide a more stable and consistent convergence characteristic. As such, we may employ multiple training samples per update as defined by this expression here. What it says is that in order for a sample S to be considered as part of this mini batch stochastic gradient descent update, it should be a member of the subset S subscript it, telling us that this is the subset of samples associated with the current iteration. So let's take a look back at the training data employed for the 0 versus 1 handwritten recognition example, the one used by the previous module. Now, for that example, we had a total of 10 training data samples. As such, n subscript s equals 10 training data samples in total. Now, let's say we're performing the first iteration of our gradient descent, and as such, we want a subset or a mini batch for that first iteration. What we could say is that it contains the first, third, fifth, seventh, and ninth training data samples, essentially all of the odd numbered ones. Now, I have defined this function that I call n that can be applied to the subset and spits out the number of samples employed within the mini batch. For mini batch stochastic gradient descent, the updated parameter array, which is again theta superscript it plus 1, is defined in terms of an average partial derivative or average gradient. This average partial derivative, this average gradient, is calculated by evaluating it for every element within our user-defined subset S subscript it. So let's take a closer look at this expression. Again, we see that the updated parameter array for the next iteration it plus 1 is equal to the parameter array for the current or previous iteration it minus the product of two factors. We have our learning rate, and then we have the average partial derivative. Now, how do we calculate this average? What we do is, well, first we have to define our partial derivative of the objective function we want to minimize with respect to our parameter array, but that's a symbolic expression. And then we evaluate it for all the elements within our current subset. So what we do is we cycle through, we sum through all the elements, starting at s equals 1 and going all the way till s equals the total number of samples within the training data set. If we're thinking about that example that we just discussed, this would be a value of 10. So we would go from 1 to 10. However, this sum has a constraint that we only consider the elements that fall within the appropriate subset. So again, if we're looking back at that example, this sum would consider only the first, the third, the fifth, the seventh, and the ninth elements. And in order to calculate the average, we divide by the n function applied to the subset, which in this case would give us a value of 5. The single element and mini batch implementations both fall within the category of stochastic gradient descent. On this page, we want to discuss an alternative, which is batch gradient descent. I'll sometimes refer to it as complete batch gradient descent. Now, once we understand the mini batch stochastic gradient descent approach, it's pretty intuitive to also understand the complete batch gradient descent. Instead of using a subset of the training data set for each iterative update, we employ the entire training data set for every iterative update. For complete batch gradient descent, the updated parameter array, which is still represented as theta superscript it plus 1, is calculated or defined in terms of an average partial derivative or an average gradient. This average is obtained by evaluating the partial derivative for every sample in the training data set. This contrasts the previous page where we just used some of the samples from the training data set. So let's take a closer look at this expression. We'll see that the form closely mirrors that from the previous 2 pages. We want to define an updated parameter array for iteration it plus 1, and that's equal to the previous or current value of the parameter array for iteration it minus the product of 2 factors. We have the learning rate alpha as well as the average partial derivative for all samples within the training data set. So we see that this sum starts at s equals 1, it goes all the way to s equals n subscript s, which is the size of the training data set. We don't have any additional constraint here because there is no subset that we have to adhere to. We insert the relevant X arrays, right? Those are the inputs associated with the individual training samples. We then complete the average calculation by dividing by the number of training samples and then take the product and move on from there. This page provides a comparison of the update expressions for all 3 of the approaches we discussed on the last 3 pages. We have the complete batch gradient descent, we have the mini batch stochastic gradient descent, and we have the single element stochastic gradient descent. All 3 of these seek to calculate an updated value for the parameter array for iteration it plus 1. They define this in terms of the previous, or we could call it the current value of that parameter array for iteration it, and from that we subtract the product of 2 factors. We have the learning rate and some version of a partial derivative. For the complete batch gradient descent, this partial derivative is the average of the individual partial derivatives associated with every sample within the training data set. For the mini batch stochastic gradient descent, this partial derivative is calculated as the average of only some of the samples from the training data set, where what sum means is defined by this subset here. And then for the single element stochastic gradient descent, our subset is essentially just a single element, which is defined as S of IT. Now that we understand the update expressions associated both with complete batch and stochastic gradient descent, I did want to use this table to compare and contrast some important characteristics related to their implementation as well as performance. We begin with choice of training samples for each iteration. We know that the batch gradient descent method employs the entire training dataset to calculate the average gradient for a given iteration IT, whereas the stochastic method employs only a subset or potentially a single element from the training dataset to calculate the update for iteration IT. Next, we discuss gradient and convergence accuracy. We observe that the complete batch gradient descent method yields a more accurate and robust representation of the overall system behavior with consideration of all training data samples for each iteration's update. The stochastic gradient descent method yields a less accurate representation of the system behavior with the accuracy per iteration largely depending on the subset size used. We rely on the law of large numbers to justify the use of stochastic gradient descent, with the assumption that after many iterations, each employing randomly chosen samples, that the stochastic gradient descent will converge to the same expected value that the batch gradient descent would yield. Next, we discuss convergence speed, and I want to begin by saying that this value is very difficult to predict. We observe that in general, overall, batch gradient descent may be slower to converge as compared to stochastic because each individual iteration requires more time to compute. We observe overall, in general, that stochastic gradient descent may be a faster alternative, as each iteration requires less time, and therefore those iterations may be more frequent. However, I do want to note that there are many cases for which the batch gradient descent is faster to converge than the stochastic gradient descent. Next, we discuss computational and memory requirements. We observe that batch gradient descent may require more computational power and memory because it has to analyze the entire training data set at once for a given iteration, and ideally or optimally, all of this data would need to be stored in RAM. We observe that stochastic gradient descent may require less computational power and memory for similar reasons. With regard to local minima, we observe that batch gradient descent is more likely to be trapped by a local minimum as compared to stochastic alternatives. Now, what does this mean? We've talked about local minima before. The objective of gradient descent is to find the inputs to an objective function that correspond to its minimum or potentially maximum, but let's say minimum input over its entire domain. This point here would be its global minimum. However, there can be other points that we refer to as local minima that to the gradient descent algorithm may look like a global minimum. So we observe that batch gradient descent is more likely to be trapped by these local minima. Stochastic gradient descent, on the other hand, provides more variation in how gradients are calculated for consecutive iterations, and this helps the algorithm better escape local minima and potentially reach the global minimum with greater reliability. Next, we discuss suitability for large training datasets. We observe that batch gradient descent is less suitable for very large training datasets inherently. This is a pretty intuitive result, right? The larger our training dataset becomes, the less practical it is to calculate a gradient for every sample of that very large training dataset and then take the average of all those values. We observe that stochastic gradient descent is more efficient, alternatively, for these very large training datasets because we have the freedom to choose appropriately sized subsets and use those for each iterative update. Next, we observe that batch gradient descent is a deterministic process. It yields the same result every time we run it, as long as we supply to it the same training data set, the same initial condition, as well as the same hyperparameters. Alternatively, stochastic gradient descent is more stochastic in nature. This is because we employ randomly chosen subsets of samples to calculate the gradient for each individual iteration or iterative update, even if we supply to it the same training data set, the same initial condition, and the same hyperparameters. It can yield different results for consecutive runs. With regard to shuffling of data from one iteration to the next, this is not required for batch gradient descent because batch gradient descent uses the entire training data set for every iterative update. There's no need to shuffle the data when it's all being used at the same time. However, for stochastic gradient descent, there is a need to shuffle the data to prevent any bias associated with the choice of samples or subsets of samples from one iterative update to the next. Next, we discuss overfitting. This is a topic I think we've addressed several times previously. We do observe that batch gradient descent is more prone to overfitting, especially for complex models. I should note that this is dependent on a number of factors, including the hyperparameters that we employ. The stochastic nature of stochastic gradient descent fortunately does reduce the tendency for overfitting, at least as compared to batch gradient descent. With regard to overall computational cost, we do observe that batch gradient descent yields a higher computational cost per iteration. However, this may be mitigated by the need for fewer iterations to reach convergence. We observe that stochastic gradient descent yields a lower computational cost per iteration. However, this may be correlated with the need for more iterations to reach convergence. As such, the effect of the method type on the overall computational cost for convergence can be pretty difficult to predict. Finally, we discuss the stability and convergence likelihood characteristics of these two methods. I do want to note that like convergence speed, this characteristic can be very difficult to predict. We do observe that batch gradient descent overall is more stable, and as such more likely to converge. However, as we've noted previously, it is also more likely to converge to a local minimum. We observe that stochastic gradient descent is overall less stable, and as such more likely to diverge, which in that case would yield no viable solution. You may remember that the last module provided an Excel spreadsheet, a simulation file, that demonstrated how we could implement our step-by-step backpropagation process and couple that with stochastic gradient descent. We employed a pretty basic image recognition example where we were essentially tasked with trying to identify handwritten zeros and ones. So what I've done is I've provided links to that same simulation file again. It's available in two places, Dropbox and Google Drive. I've provided text links as well as QR codes to make it as easy as possible to download and access these files. Now, since this module is on the subject of batch gradient descent, what I did was go back to that simulation file and adapt it to employ batch gradient descent. So as opposed to each iteration employing only one randomly selected sample from the training data set, Each iteration employs all 10 samples from the training data set. So again, it's available in two places, Dropbox and Google Drive. There are text links as well as QR codes. Now, if this link doesn't work or it stops working in the near future, I will provide a replacement in the description below. Here we have a screenshot of the updated Excel spreadsheet that implements batch gradient descent. I don't want to spend too much time discussing this here because we did devote a couple minutes as part of the previous module in explaining how the stochastic gradient descent Excel spreadsheet, how that simulation file worked, and the structure of this one is pretty similar to the previous. However, I can talk about some important differences. For stochastic gradient descent, for that spreadsheet, what we saw was that every row corresponded to a new iteration. So we have 10 rows, we have 10 iterations. For this spreadsheet, for batch gradient descent, we see that the iteration number increments only every 10th row. Now, similarly, for stochastic gradient descent, we saw the synapse weights, the parameters, were similarly updated every row, corresponding to a new iteration for every row. For this spreadsheet, for batch gradient descent, we see that the synapse weights are updated only every 10th row, and they stay static for rows 1 through 9 of every iteration. Now, what's the reason for this? Stochastic gradient descent employs only a single randomly chosen sample from the training data set in order to calculate a single set of gradients and update our synapse weights. For batch gradient descent, however, we need 10 rows because we need to calculate 10 sets of gradients, which we then average and use to update our synapse weights. So each group of 10 corresponds to a single iteration and provides the 10 sets of gradients that we ultimately employ to make our updates. This page compares simulation results yielded by stochastic as well as batch gradient descent by the two spreadsheets that we just discussed a second ago. Now, on the left-hand side, we have the results for stochastic gradient descent, which employs a smaller learning rate of 1.5. On the right-hand side, we have the batch gradient descent results, which employ a larger learning rate of 10. Now, in the top half of the screen, we have two graphs. Both have the iteration number on the x-axis, as well as the synapse weight value on the y-axis. Now, because the neural network the model used, for example, has 8 synapse weights, we see 8 lines. Now, both of these, the stochastic and the batch gradient descent, converge to similar-ish synapse weight values. In the bottom half of the screen, we see two graphs. Both on the x-axis have the iteration number, and on the y-axis have the mean squared error loss. We can make several observations here. One comes from the two graphs in the bottom half of the screen. If we compare the trajectory of mean squared error loss versus iteration number for stochastic as well as batch gradient descent, what we see on the left-hand side is that this trajectory for stochastic gradient descent is more noisy, is more jagged, and potentially less stable. Whereas on the right-hand side, we see a much smoother trajectory, which leads us to believe that this may be a more stable convergence characteristic. And it's this stability that allows us to use a relatively larger learning rate of 10. The second observation we can make is with regard to the number of iterations required for convergence. The batch gradient descent requires only 25 iterations, whereas the stochastic gradient descent requires 100 iterations. However, there's one thing to keep in mind here is that each iteration of the batch gradient descent requires more calculations, is more computationally complex, because we need to evaluate and take the average of 10 training data samples as compared to 1 over here. So that marks the end of this module that compared two optimization methods relevant to machine learning. Specifically, we discussed batch and stochastic gradient descent. Please watch the next module to learn more about certain hyperparameters relevant to machine learning, including the learning rate, weight decay, momentum, and dampening.